Good morning, good afternoon, and good evening, everyone, wherever in the world you may be joining us from today. My name is Francesco Del Carpio, and I am the CFL York Operations Coordinator. I would like to officially open the fifth session in our Mind Action, Innovation, Sustainability, and Global Partnership Speaker Series, presented in partnership with the Advanced Disaster and Emergency Rapid Response Simulation Lab, Subsphere Corporation, and APO Tracks. I would like to begin today with a land acknowledgement. First Nations peoples have lived on this part of Turtle Island for millennia, stewarding the land, the water, and all that contributes to life in this region. Today, the culture and presence of First Nations, Inuit, and Métis peoples enrich the lands and people of this territory. More than 2 centuries ago, the Mississauga people welcomed settlers to this territory, providing sustenance and engaging in trade and commerce. Between 1781 and 1820, 8 treaties were signed with the Mississaugas of the Credit First Nation, who opened their territory to settlement. Today, York University's Keele campus is located on Toronto Purchase Treaty Number 13 lands and is situated on the traditional territory of the Huron-Wendat and Haudenosaunee. Treaty history is foundational, and it is our collective responsibility to honor the land as we honor and respect those who have gone before us, those who are here, and those who have yet to come. We are grateful for the opportunity to be learning, working, and thriving on this land, and we commit to learn the truth and be active in the process of reconciliation. As this is an online event, our participants may be joining from various locations, so I strongly encourage you to learn about the traditional land upon which you are located. With this, I welcome our moderator, our speaker, and our participants from around the world. Welcome to our webinar. It is now my great pleasure to introduce our moderator, Michelle Arif. Michelle Arif is an R&D coordinator at Subsphere Corporation with a strong track record in project management and the strategic application of emerging technologies for disaster risk reduction. She holds a master's degree in disaster and emergency management and has a robust background in applied geospatial technologies and climate science. Michelle, thank you very much for moderating today's session and your ongoing help in putting this series together. The floor is yours.
Thank you, Francesco. Welcome, everyone, to our fifth session of the Mind Action webinar series. This is where we talk about innovation, sustainability, and global partnerships. Today, we're privileged enough to be joined by Dr. Robert Keeley again as our guest speaker. This time, he's here to talk to us about testing and evaluating mechanical equipment in Mind Action. So this will get really nice and detailed, and I'm really excited about this presentation. For those of you that missed the last session, you can find it on our YouTube channel and get an introduction or a refresher if you were here last time on mine action and explosive ordnance disposal. So we can post the link down below in the chat. Our speaker, Dr. Robert Keeley, is a former British Army bomb disposal officer active in humanitarian and commercial mine action and explosive ordnance disposal since 1991. So lots of experience and knowledge. He has worked in numerous countries for several government and international organizations. He specializes in project design, evaluation, and quality assurance of all aspects of mine action, explosive ordnance disposals, and has helped shape the emerging humanitarian improvised explosive device sector, the IED sector. Dr. Keeley is a member of the Institute of Explosive Engineer, a member of the International Association of Bomb Technicians and Investigators, and is a fellow of the Royal Geographical Society. So we have a lot to get through, so I won't take up too much time, but just a quick note, the chat box in this Zoom session is open for communal dialogue. Feel free to share where you're joining us from. Also, feel free to connect and comment, share your thoughts. Dr. Keeley is open to questions during his presentation. He'll have a green slide during his presentation, so when he pauses, we can get to some of the questions that have arisen during that part of his presentation. So feel free to put your questions in and we'll get to those at each green slide. Thank you so much. And with that, Dr. Keeley, the floor is yours.
Thank you, Michelle. I just want to confirm that people can see my screen.
Yes, we can see it.
Don't understand.
Okay, excellent. Well, hello, everybody, and it's nice to be back again. I just want to make it clear that this is a presentation based on my own experience. I'm not affiliated with any organization, and this isn't being presented as the opinion of any other organization apart from myself. Okay, so last time I was talking about mainly innovation in terms of detection equipment. And this time I thought it was worth talking about potential mechanical innovations in clearance and land release, and how we can think about testing that equipment to see whether it's fit for purpose. So to start, there'll be an introduction. We'll just introduce, for those of you who aren't familiar, the common types of machines. We will talk about something called the SEN Workshop Agreement, about some Japanese tests that took place in Afghanistan. And then I want to talk about the armor triangle, and how that applies to mechanical demining equipment. And then finish up with some of the problems and weaknesses in current testing arrangements. Every time you see a green screen like this, like Michelle mentioned, it will mean we're ending one of these sections, and feel free to raise any questions about the sections that you've just listened to, so that we don't get lost in the process. So then, an introduction. We talked about this the last time, and remember that we have a solution. This very old grainy picture is from a Cambodian minefield in the 1990s. And remember that we have a solution to clearing mines and ordnance. Here he is. He's paid a couple of $100 a month, and he gets the job done. So we're not starting from a blank piece of paper. So our requirement, and you'll remember this doctrine from before, I expect, we need to know how we're making his work faster, and that's about improving productivity in terms of meter squared per hour, how we can make it cheaper, reducing our cost in terms of dollar per square meter, or can we make it safer? And this is an interesting question, because actually manual demining is already generally very safe if the IMAS protocols are followed. So the product of manual demining is also generally fit for use if those same protocols are followed. So our requirement, if we're trying to make things faster and cheaper, is no overall reduction in safety. That's the minimum that we require. And there have been solutions made in the mechanical world, such as this machine, for many years. This was developed as a brush cutter. You can see it's remote controlled. There's no cab on this. It's not crewed, and it was designed to cut down, in this case, the bamboo in Cambodia that people like our manual deminer were having to spend a lot of their time cutting before they could get to work. Since those original early days, we've developed this concept called land release, and clearance is only one step in land release. So it starts with something called a non-technical survey, the NTS, which is a social science process, and that is generally, we should expect that to produce a boundary of potential contamination. That then can be followed by a technical survey, and that's a technical intervention, and it should further reduce the boundary to the actual area that is contaminated. So machines in particular potentially add value in technical survey as well as in clearance, either directly or by reducing the vegetation so that they enable, for example, dogs to be used on that cleared area. So the aim of our presentation today is to introduce testing and the evaluation of machines, to introduce some of the problems that we have and what we need from testing arrangements. So any questions so far?
I don't see any questions so far in the chat box.
Okay, well, we'll carry on.
Keep going. Okay, perfect.
Right, so common types of machines. We can describe machines by three different attributes: the type of tool that they employ, whether they are invasive or non-invasive, and whether they are crewed or remote controlled. And size is also a factor, and we'll be talking about that later in more detail. So there are three main types of tool. We have rollers, we have flails, and we have tillers, and I will introduce all of those. There's also plows and explosive hoses, although we won't talk about most of these last two in detail because they're generally used in military minefield breaching rather than mine clearance. Happy to talk about them afterwards if we've got time, but today I'm going to focus on the three main types of tool. So let's start with rollers. These were experimented with in World War II, and it's normally a set of heavy wheels, and they're designed to make the mine function as intended, i.e. the wheel rolls over the mine and makes the fuse initiate. So please forgive this rather crude cartoon, but it gets the point over. So here's the track that our roller wants to clear. Here's our buried mine. And that's what we'd normally expect most anti-tank mines to function when the weight of the tank goes over the top of them. So what a roller does is a roller is built onto the front of the tank so that the mine detonates safely in front of the tank. And here's one that I photographed in, this was in Croatia in the mid-1990s, and it's a Slovakian vehicle, and you can see the roller assembly fitted on the front. But there's something else going on in this photograph, and I'll explain what's going on there later on. So then we have flails. These were used extensively in the Second World War. It's a rotating drum with chains and hammers fitted to the end of those chains. Again, they're designed to make the mine function as intended. They were largely abandoned after the Second World War, but they were rediscovered after the Falklands War in 1982. So here's a picture from the Second World War. You can see the assembly stuck onto the front of a tank, and you can see the rotating drum with the chains on it. Now, if you look at the turret of the tank, you can see that the main armament, the gun, is pointing to the rear. And that was the big problem. Why they fell out of favour was that the tank couldn't use its gun while it was advancing towards the enemy. And this was a big disadvantage from a tactical point of view. This is one of the machines that rediscovered the flail. This is called an aardvark. There's many others now. This is taken from Kuwait in 1991. And here you can see the, I was just lucky with this photograph. We managed to capture the chains turning, and that you can see that the hammers on the end of the chains, it's striking the ground. And please note that they're striking the ground. We'll come back to that later. You can also see that the cab, because this is a crewed vehicle, is situated right to the rear of the vehicle, and there's also a protective shield between the tool and the cab. So here's our chain and the hammer on the end of it. And then finally, tillers. Tillers were first seen in the late 1990s, and they were designed to literally eat or chew up buried mines. So this was a very different idea. And because of that, the tools had to be very strong because they had to withstand the explosion if they actually detonated the mine. So because the tool was big and heavy and strong, it needed a heavy vehicle to carry it. So the first tillers were stuck onto the front of tanks or similar vehicles. So here's a picture of one. And here you can see the tool. So it's a big, heavy, solid drum with these big, heavy, strong teeth. And it turned round, and the idea is it mashes up the ground and mashes up any mines that it comes into contact with. But it's heavy. And they brought one to Cambodia while I was there, and we told them it was going to sink. and they didn't listen to us, and it sank. So this one, it took 3 days to get it out of this rice paddy. That's because it was so heavy. But a few years later, a company developed a new type of tiller, and you can see it here. And the tiller is actually hollow, so rather than being a big heavy drum, because it's hollow, the explosive force could pass through the drum, and it meant that the vehicle could be much lighter. Now, this one itself is still quite heavy, but they have made much smaller ones since. So this is this machine being used in South Sudan, and you can see that there's another blast shield separating the tool from the cab, and it can be fitted with either a flail or a tiller. Now, this machine here is another tiller, but this is an example of a non-invasive machine. So the tiller's on the arm of the excavator, and it means that the machine can park itself into, it doesn't enter the minefield. It parks itself in a safe or previously cleared area, and then it extends the arm and allows the tool to work. So we've talked about invasive machines now, we've talked about remote controlled or crewed machines, and we've introduced all three of the main tool types. But they all have a disadvantage. Essentially, whether it's a roller, a flail, or a tiller, it's essentially a cylinder. It works like a cylinder. And the problem with that is it's great on absolutely flat ground, like a football field, but the moment you get irregularities in the ground, and if a mine's in that irregularity, the tool will miss it. Similarly, if there's rocks in the ground that the machine has to drive around, fence posts, other obstacles, there's a chance that the machine will miss an area. So for that reason, we don't regard machines as being 100% effective as a primary clearance tool. You remember I showed you this picture before, and I said we'll come back to it. So here was our roller, but what this has got here is there's a plow added behind the roller, and this was not improvised. This was done from the factory, and the reason the plow's there is to catch any mines that are missed by the roller and then push them to one side. So this demonstrates that even the manufacturers of this equipment in those days recognized that the rollers weren't 100% effective. And there's more. So here we have an anti-personnel mine. This is made in Italy. It's called a VS50. To give you an idea of scale, there's a footprint. And what's really interesting about this mine was that, as you can see here, there's this, where the arrow is pointing, there's a tiny little rubber hollow sphere there with a pinhole in it. And what this means is that when you step on the mine, and I wouldn't recommend anybody does this, but when you step on the mine, what happens is there is a tiny, tiny delay. The air, as the mechanism's trying to work, it's being held back by the air escaping through this tiny hole. It only adds a fraction of a second delay, but it means that and it was built in for a particular reason, which I'll explain now. In the 60s, various armies started developing thermobaric or fuel explosive weapons, and they were designed to be detonated over a minefield, and the overpressure from the explosion would detonate all the mines underneath it. So as you can see in these 3 steps of this diagram, which I lifted from the internet, at first, the weapon is normally delivered by aircraft, but it can be delivered in other ways. As it gets close to the ground, it releases a vapor, something like petrol, and that spreads out into a cloud, and then a millisecond or a microsecond later, there's a second explosion that ignites the cloud, and it causes a blast and an overpressure. And the idea is this overpressure stamps on all the mines in the minefield. Now, thermobaric bombs have gone on to be used for other things, but this is what they were intended for. And so what we see after that, this being invented, as is normal happens, people invent a measure, then somebody invents a countermeasure. There is a whole generation of weapons, such as this Soviet era mine called the PMN2 and that VS-50 Italian mine that I showed you before. They have these defensive mechanisms against blast overpressure. Now, it's not a long enough delay to mean that a person standing on the mine can step away from the mine. That doesn't happen except in Hollywood. What it does mean is that short, sharp impact that you get from something like a flail doesn't always detonate these mines. These mines weren't designed to be flail resistant, but they are. And in fact, when we did some tests on that on the VS-50 in Q8 in 91, the team conducting the test found that a flail was only 50% effective at clearing the VS-50 mines. So we had to rethink about how we were going to use the flails as a result. So that's another reason why we can't always consider machines as 100% effective. But they still have a use, and we can talk about that more. But I want to move on now to this thing called the CEN Workshop Agreement. But before we do that, are there any questions so far?
Yeah, just checking in. I don't see any in the Q&A box, but a reminder to everyone, feel free to pop them in. I know we're getting a lot of information really fast, so yeah,
Sorry,
feel free to ask questions.
Quentin has their hand raised, so I'm gonna give them
Okay.
permission to talk. Yeah, they might want
Yeah,
to
sure.
ask a question. So, Quentin, you can go ahead.
So, Robert, just a quick question on when you classify the machines by like type of tool, invasive or not, crude or not, um, does and you did actually talk about this when you talked about combinations of tools, right? So a combination of a roller and a plow. How effective is that roller plow combination?
That's an interesting question. The Soviet military obviously thought it was a good idea because they built the thing. And plows are used in various NATO armies as well. The problem is with the plow is that it doesn't clear anything. It pushes it to one side. So it becomes somebody else's problem. And what also happens is because of the nature of plows, is it then puts that mine into a berm of soil that's been turned over.
Right.
So we've destroyed any pattern in the minefield, and we have now made the job altogether much, much harder. And in
Right.
fact, at one point, the American State Department had to release a contract, I think it was in Angola, to clear an enormous berm of mines that had been caused by somebody driving a plow up a road and putting all the mines in this soil berm. So from a tactical point of view, would I rather go up a beach against Rommel after a plow or after having to go up it on my belt buckle with a bayonet? I'd much rather follow a plow as a soldier's point of view. But in
Yeah.
terms of humanitarian clearance, they're really not very useful.
Right. So the plow roller combination is a breaching technique, not a
Yes,
clearing
exactly.
technique. Okay.
Yes.
All right,
Good
thanks.
question. Thank you. Any other questions? Good. Let's move on then. So the CEN Workshop Agreement, or CEN CWA 15044, if anybody wants to look it up, came about in the early 2000s. Now, CEN is the European Standards Organization. I think it's Centre Européens Normalisation. I think that's the French for it. I could very well be wrong, but it's the European equivalent of International Standards Organization. And for various reasons, they dabbled with a series of mine action standards in the early 2000s. One of these was a standardization or a testing arrangement for mechanical demining equipment. This was largely picked up and developed in the Swedish Engineer Centre in Swedac, obviously in Sweden. And it was designed to test effectiveness and survivability of machines. Survivability, crew survivability, was tested by shooting the cabins of vehicles with 7.62mm ammunition, which was held to be similar to the effect of a piece of fragmentation from a mine. And machine survivability was tested by detonating 7 kilograms of TNT, the equivalent of an anti-tank mine, detonated under the tool of the vehicle. Now, if that was a non-invasive machine, it would be tested under the tool, and similarly on an invasive machine, it would be tested under the tool. So that was whether they tested whether the machine could then work, or if it was damaged, how much time was needed to put the machine back into use. Effectiveness was done by, they built 3 lanes, one of sand, one of gravel, one of soil, and each had 30 targets in the lane, as they were trying to establish some sort of statistical significance with 30 targets. And Swedish AP mines that had been kept in inventory for testing purposes, which they were allowed to do under the terms of the Anti-Personnel Mine Ban Treaty, but they had been rendered safe. They'd taken the main explosive charge out, and they'd left the detonator system in, if I recall, so that the mines could be inspected afterwards to see whether they'd functioned. But they also added something called a witness plate, and I will talk about that in a bit of detail because it's very interesting. So here's a cross section of the soil in our lane, and they added these witness plates across. They were a piece of timber across the whole width of the lane, about 30 centimeters deep. And the idea was that they then put these witness plates along the lane, as I've shown here. And then the idea would be that after the machine had processed the ground, they could recover the witness plate and see how far down the tool had managed to penetrate, and therefore potentially destroy the mine that was underneath. And this was the Swedes were pushing a particular machine at the time. This is it. This is called the Scanjack, and you can see it's actually got 2 flails, one behind the other, and it's really quite a very large machine. And we'll talk about the implications of that later. There are limitations to this concept. First of all, it was very difficult to replicate because who was going to be able to get hold of these Swedish AP mines if they wanted to do their tests somewhere else? And those of you who are scientists and have got bigger brains than I have, you know that the ability to independently replicate a test is very important. There was no test of maneuverability. There was no test of ground preparation, i.e. a machine like the one I showed you earlier, which is not designed to detonate mines, it's just designed to remove vegetation. There was no test of acceleration on the driver in a crewed machine. And there was no test of overpressure in the cab, again on a crewed machine. But ultimately, the biggest problem for me was that there was a fundamental misunderstanding of how flails work. And if we go back to this picture, remember I told you that the idea of a flail was originally to make the mine function as intended. If you were to go and dig up your garden today, you would not do that with a chain with a steel ball on the end. Steel balls are fundamentally not very good digging tools. So they weren't intended to dig the mine up. But what somehow had happened was that people had misunderstood in the development of that large Swedish machine, and also the testing arrangement, they'd misunderstood this. And what happened was the inventors of that Swedish machine were convinced that their job was to smash up the mines like Attila does. And so in order to do that, they had to have a huge amount of power to get those hammers of that flail underground. And that meant 100 horsepower per meter of tool, which is an enormous amount of power. And it pushed them down the evolutionary path of a very big machine, which actually wasn't necessary at all. Here's an example of a modern flail. I took this picture in Ukraine last year. Now, there's two things. One is this is a remotely controlled device, as you can see. So it's not crude, but it's a flail. But if you look at the end of the tools, the tool, it's no longer a hammer. It's been fitted with blades so that it can dig down and achieve the requirements of the SEN workshop agreement. And frankly, this was totally unnecessary because the idea is to make the mine function as intended. But this is the problem with this this workshop agreement, is it's introduced systemic bias into the way people are now trying to design machines, because it doesn't need to do that to be effective what it does. Okay, any questions so far?
Yeah, we just got one.
Okay.
Let me. Yeah, so in the chat box, these are heavy machines. Could you please tell the situation or development of robotics, AI, and landmine clearance right now and in the future?
Well, AI, it's an interesting question, and it's probably worth a chat all from itself. In terms of, for example, the machine I've just shown you, this is a robot. It's controlled by somebody carrying something very similar to a Game Boy controller, but it's a robot. There isn't very much requirement for AI in this. It's quite agricultural as a concept. I mean, AI is essentially in this case a way of absorbing information from various data sources and making decisions that could be necessary and very helpful in other stages of land release. But in terms of actually employing these tools, not so much. But it's worth a conversation, and we will touch on it a bit later on, if that's okay.
Thank you. Yep, that's the question we had.
Okay. So Japanese testing in Afghanistan. The idea was this was something that was done in 2004. It was a Japanese organization called JIX, and they had 9 machines to test, and they hired me in to design a test protocol for these machines in Afghanistan. The tests we devised were SEN compliant. They included all the SEN requirements, but we also added tests on maneuverability, and we added tests on productivity. And we'll talk a bit more about those. So here's just an example of one of the machines. This is if you look very carefully underneath, you'll see this is a tiller. And as you can see from reading it, this was developed by Kawasaki. And just on the right-hand side, you see it was called the mine bull. There were some complications with some of these machines due to something which would take really a long time to explain in detail, but the machines were designed only to clear anti-personnel mines, and the problem is that there weren't many minefields in Afghanistan that we could guarantee didn't have anti-tank mines in them as well. And that was a communication issue between the Afghan Mine Action Program and JIX. But these 9 machines turned up. So we included a test on maneuverability. We took 30 degrees as an arbitrary measure of could a machine drive up, drive down, drive across the 30-degree slope, and could it work in a 30-degree slope in the same way. So this was us laying out some lines. Now, the other thing we did, rather than witness plates, was because we couldn't mine Afghanistan, what we did was we essentially, I call them frangible boxes, but essentially it's a Tupperware box filled with, and this picture gives you an idea of the scale. and it's broadly the same size as a PMN mine, and we filled it with powder paint. And the idea being was that we buried it underground in the test lanes, and if the machine hit the mine, what we'd expect to see, sorry, I'll just go back there. We expect to see some damage to our Tupperware boxes, and we'd expect to see the paint scattered about. So it was a safe test, and we could benchmark the boxes by putting weights on them to see whether they broke at the same operating pressure as an anti-personnel mine might detonate. So that's how we benchmark the targets. So it's a very cheap and very effective, very visually effective way of testing the machines. But we also added a productivity test. And what we did was that we gave each machine a hectare of ground and said, there may or may not be some mines in here. And there may not, we're not going to tell you how many there are. And you can now clear this piece of land, and you can take as long as you like and tell us when you're finished. So in other words, we forced them to make a decision about how fast they would go over the land so that we would get an idea of whether they were cost effective or not. And we'll talk more about that in a minute. So any questions so far on the Japanese tests?
I don't see any in the chat box, but let me check.
Okay.
Hand raise. Anyone's got their hand up? Nope, I don't see any.
Okay. So
Thank you.
where this comes in is this thing called the armor triangle. So here we have a tank, and there are three attributes to any armored vehicle, any armored fighting vehicle. We have to consider its firepower, we have to consider its maneuverability or mobility, and we have to consider its protection. And these things are a trade-off. For any given size vehicle or any given size engine, if you want more protection, for example, you have to trade either firepower or trade mobility. Because if you want more protection, that's more armor plate. If it's got more armor plate, it's heavier. If it's heavier, it's less mobile. If you want more firepower, again, for any given weight of vehicle, you have to either trade protection or trade mobility. And this is the armor triangle. So the implications of that applies to these, the same idea applies to these mechanical demining equipment. To get more power to the tool, you need either a bigger power plant. The bigger the machine, the more expensive it's going to be, and it starts to become cost effective, because remember, we're comparing it to that manual deminer and the amount of land that he or she can process in any given hour. So this machine, which I showed you earlier in Afghanistan, was actually the most protected. It was the only one that survived the 7 kilogram explosion under the tool, but it took 44 liters of diesel per hour. And that in Afghanistan in 2004, a liter cost $3 because it had to come all the way up, from the south. And that was more expensive than the manual deminers it replaced. So although the machine was actually very effective and now it works, it was not cost effective. And this is one of the issues we're testing these machines. So any questions about the armor triangle? Okay, let's go on to the last section. The current test problems. Remember our catechism. We want it to be faster, cheaper, or safer. The SEND test had no test on productivity. There was no measure of cost effectiveness in the test, no test on maneuverability, and it needs much better testing on survivability, particularly for crewed machines. Testing for the ability to withstand acceleration or the ability to withstand overpressure. And that witness place test protocol that was included introduces a bias into the test which pushes towards heavier machines, which may be less cost effective. And the frangible box system is an idea that replaces the problem of replicating the test elsewhere, because the original test was designed around those Swedish anti-personnel mines. And again, like any test that we do introduce, must be statistically significant. Remember, with our equipment, that we can test it in a laboratory or on a football field, and it looks safe and it looks effective. But when we actually start using it in the field, we get environmental problems and we get human factors involved. And so it may be that our machine is safe in the laboratory, but but unsafe or ineffective in real life. Remember that machine that sank in Cambodia, for example. So we have to make our tests as close as possible to the real thing. So another point I think we need to emphasize is, what if it's not clearance? We need to design the test against intended results. So, for example, a brush cutter, which is not intended to detonate mines, we need to think about things like the density of the vegetation that it's cutting and the rates of clearance that it's going to, the vegetation clearance that it's going to have. We can't just apply the SEN workshop agreement standards to it. And we must always consider cost effectiveness, because if it's more expensive than our local deminer, we're better off paying for that person to do the work. So we have to always consider, what are the benefits of this new technology compared to the current way that we do business. And another thing which came up again in 2004 was environmental issues. We have to remember this, that soil is not dirt. Soil is a complex ecosystem, and machines can destroy it. We can do something called pulverization, i.e. we just turn that ground into dust and it blows away. We can create something called hard pan, and we can create something called shear. These are both common environmental problems from mechanical equipment. Here's a picture of a piece of ground in Cambodia, a photograph taken in 2004, after some tests that an organization called MAG had done in 2001. And this piece of ground, as you can see here, is packed solid earth and nothing's growing on it. Now, Cambodia is one of the most fertile countries in the world. And for this piece of ground to remain barren for 3 years shows the effect of things like hard pan and shear. We can destroy the village in order to save it, as was apparently said in Vietnam once. So some final thoughts. Machines have a role as ground preparation, but remember the cylinder effect, or they won't clear every single thing in that ground because of problems, irregularity in the soil and other problems like that. We need to understand how machines tie into land release. We need to consider something called their effectiveness against something called all reasonable effort and any residual risk. The question of all reasonable effort is a huge subject, and it's a subject for another day. I can't really do it justice in the time we've got left. So to finish, we've talked about these 5 things, the pillars and the products. We've talked about faster, cheaper, and safer. We've got failure to situate in. We are, for innovators, the key point about this, and this came up in the first presentation, of if we don't visit the ground, if we don't understand our problems, if you don't talk to us, you won't understand how your device works for our requirements. And you have to prove to us that it works. You've got to solve our problems. Key metrics: faster, cheaper, safer, and benchmarking. Those are the same whether you're developing a detection device or a machine. And remember that mine action is a system. Area clearance is one of several activities. The earlier in the system we had more value, but please learn the system first and save your own money developing things that may not work. So, final chance to ask any questions or open up a discussion.
Yes, now we have some questions and comments rolling in. So I can, yeah, I'll just, the first one was a comment about machines needing maintenance. Do you have any thoughts on expanding on that?
Okay, that's a really good point. And where that ties in is there's an idea of understanding how to benchmark the productivity of a machine. We've got the potential theoretical capacity of a machine in terms of meters squared per hour. And then from that, we've got to take away the environmental factors and human factors. So what we're left with is a net product of what it can do. And inside that issue of theoretical square meters per hour, there's the question of downtime, or as equipment people would talk about mean time between failures. So if you've got a machine and you hear somebody say, oh, we can do 10,000 square meters an hour. And then you say, okay, what you've done there is you've cleared 5,000, you've cleared 100 square meters and you've extrapolated it. And you've said, oh, I've done 100 square meters in 6 minutes. Therefore, I can do 10,000 square meters in whatever it takes. And the point about that is that that's not how it's done, because it has to allow time for maintenance and they have to allow time for failures. This ties back into the way it's measured. And so it's a really important question of maintenance. Similarly, if it does, in one of the things we looked at in Afghanistan, and it's in the SEN workshop agreement, is if you detonate that 7 kilogram charge, how long does it take to put that machine back in the field again? If it takes 3 weeks to repair it, you've got to ask yourself whether that's worthwhile. You want to see it being used in a very short time.
The second question comes in from Saw. In a civil war or conflict area, is it very difficult to use this type of heavy machinery? What's your idea for the situation?
Well, we get into a problem now of, well, first of all, don't forget, not all of these machines are very heavy. That yellow one I showed you from Cambodia can be towed on a trailer by a pickup truck, or certainly a light truck. So they're not always all that very heavy. But there's a bigger question of whether you can do any demining in a civil war. I mean, it's one of the problems that Ukraine faces at the moment, is that they've got such a massive problem. They're having to recover a very large area of their country that's potentially contaminated, and yet still fight a war. And there's been terrible casualties, even quite recently in Afghanistan. Sorry, I keep saying Afghanistan, in Ukraine, of deminers being killed. So it's a bigger problem than whether you can use a machine or not.
I did see a hand raised. It just got lowered, but I was just going to go through the questions. Do you want to ask your question? And Francesco, do we want to unmute that person that had their hand raised?
Yeah, I saw that the hand was raised, but I can't remember the name. If they raise their hand again, I can give them permission to talk.
And Yama Bosco, I think it was. But yeah, if you have that question, feel free
Oh,
to
okay.
raise.
Yeah, I think
Yeah.
it was as well. That sounds familiar here. And Yama, if you want to go ahead. Well, I've given them permission to talk, so if maybe they've stepped away for a minute. So if you want to continue with the questions when they're back, I'll just leave their permission open.
Perfect. Okay. So the next question comes in from Neil Thompson. Great strategy on the TNEP with blind testing for organizations. Would have made the organizations a little nervous, but at least you got true and accurate data. I guess that might be a comment instead. But do you have anything to add to that one?
Well, yes. I mean, the whole point of that testing that we did in Afghanistan was it was a blind test. They didn't know where the targets were in the block of land that we gave them. In the lanes, they know where the witness board. The problem with the witness board system is that you know what you've got to do. You're watching it. And whereas the piece of ground that we gave them with the buried plastic pots in, it was indeed a blind test. And so the organizations had to, the machine users had to, they had to make their own judgment about how to use it.
Okay, perfect. Another question has come in. Has the DRDC field work over 30 years come up?
Well, that's interesting. And Carl, after this is one of the reasons I never use the word expert, because I don't have the faintest clue what that is. I mean, if you want to step in and explain to us what it is, I'd be really happy. I don't know. I've never heard of it.
I'm not familiar either. That's why I kind of paused that. Yeah, Cal, if you want to unmute your mic, feel free to ask this question. I don't think we've gone over this. And then we have another one coming. Oh, sorry. Yeah, go ahead, Cal.
Now I can unmute. Thank you very much. Can everybody hear me?
Yes, we
Yes.
can.
Okay. Defense Research Development Canada at Suffield has had a long-term program for demining technologies over the last 30 years. And I'm one of the research council's sort of interface to that and commercializing as possible some of that technology. So there's a bunch of stuff there and a lot of history of what has been tried to do a lot of this work, including, I think, back to Afghanistan too. So yeah, if there's access to the work that they've done over the years, it just stops us from reinventing wheels that have already been tried and failed. So anyway, I just want you to know that that is there. If you have contacts into Defense Research Development Canada, that'd be a good place to probe around and say, okay, what have we done on the demining technology side? Because they've put a lot of work into that over a lot of years for NATO.
That's really interesting. And actually, now that you explained what DRDC is, I understand it a bit more. When I was working in Cambodia, the Canadians appeared with an ultrasonic mine product or mine probe, and the idea was that if you're prodding for mines in ground where you can use a podder, if it's soft ground like a rice paddy, then the idea when you're prodding, you're feeling for something hard against the probe, so that you think, oh, there's something there, I'd better do something about it. Which means under normal circumstances, we dig it up, see what it was. Oh, it's a rock. Okay, carry on prodding. What's that? Oh, it's another rock. What's that? Oh, it's another rock. And eventually you probe something and you think, you dig that up and it becomes a mine. And then you think, right, now I've got to do something about it. So the idea was to deal with these false positives, was that they built this ultrasonic product that when it touched something that wasn't stone, it would react in a different way. It would give a different signal. I can't remember whether it lit up in a different way or it buzzed in a way, but they had this great gee whiz moment. This is what they were going to do. And the problem with it was that when you give a tool like that to an actual deminer, and this came up with a particular metal detector a few years later, you're paying this person a couple of $100 a month to clear mines, and you've taught that person that every time you feel something hard, dig it up. And now suddenly what we were, from the safety of our laboratories or the safety of our office or the safety of our air-conditioned Land Cruiser, what we were telling these people to do now is, right, when you get something hard, you can ignore it unless it does this particular thing. And at this point, and I can't be rude on this presentation, but you can imagine the words that were said by these deminers. They basically said, yeah, right, I'm going to do that, am I? Because they're the ones taking the risk. And it failed because of the human factor. So the device itself may have worked really well, but it failed because of human factors. And it's an example of, and I'm not picking out the Canadians particularly because we've all seen machines developed by all sorts of people. But the reason why a lot of these innovations don't work is when they meet the ground, something happens, particularly the human factors, which means that it doesn't actually go forwards.
Yeah, the real challenge that they worked with for years at Suffield is actually keeping the people safe as you deploy this stuff into the field, and using teleoperated machinery and all kinds of remote controls and lots of approaches to that. So yeah, it's an ongoing problem, and actually making sure people have things that they can use quickly, easily, safely is a huge issue that is still going on, obviously. Hey,
Yes.
one other thought we've actually heard about. We've got companies in the agricultural sector actually supplying map information through agricultural channels into Ukraine, so that they have safe transit routes. They know where to drive their tractors. It's little stuff like that matters a lot. But anyway, I'm just hearing about some of that in the background from some of the industry leaders.
Absolutely. And I mean, the amazing developments in mapping are really useful. There's one particular team that I know that are actually mapping where the detector head of an individual deminer goes, so that afterwards you can be sure that that detector head has passed over every square inch of ground that they're supposed to check, which I think is a really good quality control technique. But Carl, I'm gonna say that we've got a couple of other questions come up, but if you want to talk offline about some of these ideas, I'd be very welcome for it.
Yeah, happy to. Go ahead with the other questions.
Thank you. Yeah, feel free to connect afterwards as well. We've got an anonymous question here that comes in considering their relative strengths and weaknesses of rollers, tillers, flails, have any been shown to be cost effective once you include follow-up methods required by IMS? If so, which is the most cost effective and under what conditions?
That's a really good question. When I did exactly part of that for my PhD, and in the end, I found that remote control machines tended to be much more cost effective than the big crude machines in general. And the reason was that particularly in places like Cambodia or Laos, where the soil's so fertile, was that the bigger problem with the big machines was that they were trying to clear ground so that manual deminers could follow up. And what would either happen is that they would work so fast that by the time the deminers caught up with them, the vegetation had grown back. Or because of that problem, they would clear a little bit of ground and then park up, which meant that, again, back to this human factors idea of the potential speed of the machine, less the environmental factors, less the human factors, it meant that the machine was only working to a tenth of its potential productivity. So there was no point in having a big machine because 9/10 of the time it was idle. So I have found that the smaller machines tend to be more useful than the bigger ones, basically on the concept of just in time. And in terms of the tools, these lightweight tillers have been very effective. I know that people are very happy with those and they're very popular. The flails have a purpose as well if you can get away from this idea that you're not trying to excavate mines with a flail. The rollers less so, and the problem is this cylinder effect with rollers is that the risk is that you get false negatives with it.
Sorry, I just had a look at the time and we're running quite off schedule. We do have more questions coming in, but Francesco's put his email down in the chat. If you guys want to connect with Dr. Robert Keeley, feel free to email Francesco or Dr. Keeley himself, and I'll be happy to answer some of the questions that we have coming in. They look great. But I just want to say from our end, thank you so much to everyone that's joined here today for the 5th session of the series, and we look forward to seeing you at the next one. And thank you so much to our speakers and panelists and attendees. Thank you so much.
Yeah, thank you, everyone. Just to echo Michelle's closing words there, thank you so much for joining us. Thank you so much, Dr. Keeley, for the presentation. Thank you, Michelle, for moderating, and Shahab for helping us put all this together, and for the partnership with Subsphere. And yes, my email is in the chat, so if we didn't get a chance to answer your questions, please send me an email with those questions and I'll pass them on to Dr. Keeley and we'll get those answered for you. And just as a reminder, this is a recorded session. So I did earlier share the link to our YouTube channel, or to the YouTube playlist where you can find all of the previous sessions. And this one will also be added in the next day or two. And this is also a monthly series, so we will have another session in August. So please do continue to share the information about this series with your networks and with anyone who might be interested. Registration is always open and free. So with that, just one last big thank you to everybody. It was a great session, and we will see you all in August. Thank you so much.